Image labeling is boring, takes time, and costs a lot of money. But with recent advancements in computer vision, namely introduction of very capable zero-shot object detectors like grounding DINO and groundbreaking models like SAM, you can actually automate most of that process. For most of use cases, you can literally write a Python script that will do 95% of the work for you while you are just chilling, and your only job is to go through those annotations at the very end, maybe add or remove some polygons here and there. But the truth is, you just saved a ton of time. Okay, so let's dive in and let me show you how you can use Python to fully automatically annotate your raw images or to convert your bounding boxes into segmentations. And stay around till the end of the video because we have quite a big announcement to make. Okay, so let's open the notebook first. The link to the notebook is in the description of the video, but you can also find it in Roboflow Notebooks repository. It is located in the computer vision skills section, the first from the top. So let's open the notebook right now. It will redirect us to Google Colab. Great, and before we start, let's zoom in so you would have easier time following the tutorial. Here in the top section, you can learn more about the models that we are going to use and the general idea behind the notebook. So as I said in the intro, we will use a combination of grounding DINO, a super powerful zero-shot object detector, and segment anything model that can produce masks based on the prompt. And importantly, you can use bounding box as a prompt. So we will use the output coming from grounding DINO to prompt segment anything model. And the first thing that we need to do is run NVIDIA SMI just to confirm that we have access to GPU. The command should give you the same result as the one visible right now on the screen. And if that's not the case, then most likely you are running your notebook in a CPU mode, not in a GPU mode. You can easily fix that by following the instruction in before you start section. The model should run regardless, but it will be significantly slower on a CPU without any optimization. Great, now we need to set up our Python environment. Feel free to skip that part using the chapters in the YouTube video. It shouldn't be very long, but it can be boring, especially if you watched our grounding DINO and some videos already. For all of those who are still here, what is happening right now is we are installing grounding DINO. To do that, we clone the repo, we check out the latest hash at the time of recording that video. This is to make sure that the notebook will run, even if some breaking changes will be introduced in the actual repository. And at the end of that cell, we install all project dependencies, and this is the part that most likely will take a few more minutes to complete. So let's speed up that process, shall we? Great, the next thing that we are going to do is to install segment anything model, and in that case the process should be significantly faster. Just a few seconds if I remember correctly, and we are done. Just two more dependencies to install, I promise. The first one is supervision. This one is actually installed as the part of grounding DINO repository, but its version is fixed to quite old one, and today we are going to use one of the latest features. So we need to uninstall the old one and install 0.6.0. And the other one is Roboflow, as we are going to use datasets from Roboflow Universe, but also upload our automated annotations into the Roboflow backend so we can refine them in Roboflow Annotation tool. Awesome. Those who watched our recent grounding DINO tutorial probably remember that to run that model, you need to have two files, the configuration file and the weights file. The configuration file is part of the repository, so we have it already. The weights file need to be downloaded, and we run wget to do that. Similar story when it comes to SAM. Once again, we need to wget our checkpoint. And when that is done, we are pretty much ready to load both of our models into the memory. We start with grounding DINO, and during the initiation process, it will download few more weights, probably for the backbone. Nothing too crazy, so that process should be done relatively quickly, I hope. And after just a few seconds, we have it. Okay. The second model, SAM, I'm using the larger version of the encoder. It's slower, but it produces better quality of the masks. And that's our primary objective here. It is also worth to remember that the image encoding part will only run once, regardless of the amount of bounding boxes on the image. So in reality, in that particular use case, even if that encoding part will take a second longer, it's not a problem for us. Great, the Python environment setup part is done. We can finally play around with those models and hopefully auto-annotate our data. As usual, I will use my images as an example, but feel free to upload yours into Google Colab. You just open up File Explorer on the left side and drag and drop your images. The one thing that you need to remember about is to put them into the data subdirectory. It will be simply much easier for you to follow the next steps of the tutorial because you won't need to manage your file paths on your own. Everything should work out of the box. Great, so I'm setting up the data directory and downloading a few of my images into it. And we can pick one of them and use grounding DINO to produce zero-shot detections for selected classes. Here's the list of classes that we are going to use. So obviously feel free to change the image or change the list of classes, or generally speaking, play around with the parameters of our inference. Here is something quite interesting. So we noticed that with a little bit of prompt engineering, adding word all before the name of the class to be specific, we are getting significantly better quality of the detections. Without it, especially with longer class lists, models tend to return only one instance of object of specific class. But that small hack pretty much ensures that you will get all of them, at least in most cases, because you never know. You can learn more about it from our blog post. The link to that blog post will be in the description below, but in the meantime, back to our video. Now we can put grounding DINO to the test and run our first zero-shot detection on example image. That might take a little bit of time, especially the first time around. It is a pretty common problem that the deep learning models need to warm up. But overall, we got pretty good result. Maybe the only weird thing that happened is that we got double detection for the dog. And the reason for that is that my leg is weirdly splitting the dog in half. So we got one detection for the whole dog and one detection for the part of the dog that is above my leg. Those are certainly the common problems of the object detection, regardless of the model that you are going to use. Nothing unusual happening here. Now we can use our freshly obtained bounding boxes to prompt SAM. So we wrap the whole segmentation part into the separate function. And maybe some of you remember that a few minutes ago I said that the encoding part is running only once for every image. And now we can clearly see that it is the case. We run the encoding and then we loop over the bounding boxes to prompt the model. So now let's run that logic and take a look at the result. We can see that for every bounding box that we originally extracted using grounding DINO, now we have the corresponding mask. That visualization is sick, but it's pretty hard to see the detail of every mask. Let's plot our results in different ways so we can take a deeper look. Here we see every mask displayed on a separate plot along with the corresponding class name. Every individual image is basically the result of prompting SAM with different bounding boxes. But interestingly, if we zoom in, we see that some of the bounding boxes produced multiple masks. This is something that we will need to handle when we will save those masks into some common annotation format, in our case, Pascal Voc XML. We will save each of those detached masks as a separate object. It will happen behind the scene, but it's worth to know that it happened. Okay, at this point, we know how to process and annotate a single image. Let's do the same for the whole set of images. Similarly as before, we defined our class list and other parameters of zero-shot detection. And below we have the code that we will use to automatically annotate all the images. I will just let it run and explain what is happening in the meantime. However, it's pretty straightforward. We are listing all the images in the directory. We load the image using OpenCV. We run grounding DINO to extract the bounding boxes, and then we filter out all the bounding boxes that don't have assigned class. It can happen from time to time, so to prevent any errors in the later part of the notebook, we are simply discarding those bounding boxes. And at the very end, we run SAM to extract masks associated with every image. Now, the cool part is we can actually plot all of those masks on corresponding images. In my case, it's pretty simple. I only have 8 images, but keep in mind, if you have larger image set, that may actually take a lot of time to finish. So either skip that cell completely or just pick some images from your dataset. This is really cool because we can get a lot more insight before we will save our dataset to Pascal Vogue XML and send it to Roboflow, and get a lot more intuition about the expected quality of our annotations. In case of any problems, we can play around, change the parameters of our zero-shot detection to ensure the best possible predictions quality. Now we are finally ready to save our predictions. Like I said before, we will use Pascal Vogue XML to do that, and we will use one of the latest features of supervision to make it as simple as possible. There are 3 very important parameters at this stage, and those are mean and max image area percentage and the approximation percentage. They can have high impact on the quality of the annotations that you will see in the Roboflow editor, so I guess it's worth to spend a few seconds to give you a deeper understanding. So a few minutes ago, I showed you a chart where you saw each mask as a separate image. I mentioned that we will need to take care of each detached part of that mask as a separate object, and those parameters allow you to customize that process. The first 2 filter out masks based on their area in relation to the whole image. You can use them to drop masks that are too small or too large. Sometimes, especially for small images, grounding DINO produce bounding boxes that pretty much cover the whole image. On the other hand, in many cases, SAM, when it's not sure what to do with given bounding box, can produce mask that is detached into multiple elements, even 20 or so. You can get rid of both of those glitchy types of detections, as most likely they are not what you are expecting, using those 2 filtering parameters. The third parameter will steer the amount of points that will constitute your annotation polygon. And now you may ask, what annotation polygon? Up until now, we were only working with masks. You see, most annotation formats actually don't use masks. They convert those masks into polygons that pretty much cover the same area. This is exactly the case for Pascal Vogue XML. And obviously, depending on the amount of points, that polygon may be more precise or less precise. So some of you, I assume, right now have another question. Why would I limit the amount of points in my polygon? I guess the amount of points in my polygon directly translate into quality of my mask. Well, not exactly, and not every time. Sometimes, especially for high-resolution images, that conversion between mask and polygon may cause a lot of glitches and weird geometry of your polygon. So it's actually better to keep 25 or 50% of the points in your original polygon and keep the geometry simpler, especially in the cases where you don't lose a lot of precision. But you need to remember not to drop too many points, because in some cases you may end up with triangles or rectangles. And the second important factor is the size of your annotation files. If you have thousands of points in your polygons and you have tens of polygons on a single image, that file for every image may grow and it will be hard to work with. Sure, it's a trade-off. In some cases, you actually aim for this level of precision, but actually in like 99% of the cases, this is not what you need. Okay, enough of the talking. Let's finish the conversion and upload our annotations into Roboflow. But before we do that, let's open up the File Explorer and take a look at the content of data directory. So you can see that I have 8 images over here. And when I save my mask to annotation files, I will actually create separate XML file for every image. And this is exactly what we see right now in our File Explorer. We created Annotations directory and we have 8 XML files in it. Now I can download one of those files onto my hard drive and actually show you the contents of that file. So let's do it. Let me just bring the VS Code editor on my shared screen, and yeah, here's the content of the XML file. We can see the name of the associated image file, the resolution of that image, and here in the later part of that file, every object has a separate tag. In it, you can find the bounding box and the polygon. Now that's pretty straightforward. We can now close the VS Code And given the fact that we have XML files created for every image, we can now proceed to upload them into Roboflow for further refinement. We will use Roboflow pip package to do that. So let me first change the name of the project and its description, and we can run the next cell to actually create that empty project in my Roboflow workspace. So I followed the link in the Jupyter notebook to authenticate myself, generate the token, copy and paste it in the notebook. This authentication is obviously required because I will be executing things like creating projects and uploading images and annotations into it. Now that the cell is actually successfully executed, I can sign in into my Roboflow account, and sure enough, I can see the empty project named YouTube tutorial, and soon we will fill that project with images and annotations. So we just go back to our Jupyter notebook, press Shift Enter, and wait a few seconds for our images and automatically generated annotations to be uploaded into the Roboflow account. Looks like the process is completed. Now we can go back to our project and go into the dataset, and we can see that the images and the annotations are here. We can quickly take a look. And when we zoom in, we can see that some of the masks, not all of them, have those irregular edges. This is unwanted effect being the result of basically low quality of the mask being converted into low quality of polygon. We can solve that problem partially by dropping a larger amount of points from the polygon, which will indirectly have the result of smoothing the edge of the polygon. Let's switch the view to layers, because I guess it's easier to examine the scenes where we have multiple polygons of multiple classes. We can see the shoes, the backpack, the nose of the dog, the ears, part of the person, because the person got splitted into two parts as the backpack basically divided that polygon into two parts. And interestingly, we have two detections for dogs, so we can simply right-click on one of the polygons and delete it. And that's pretty much all the data cleaning for that particular image. Let's maybe take a look at one more. So here we have the cup. It's pretty cool. The chair, which is actually not chair, but in that particular case, maybe we can assume it is. Shoes, ears, dog divided into two parts, similarly as the person divided by the backpack on the previous image. I'm certainly very happy with the quality of the predictions for that image. Okay, so that's it. Zero-shot annotation with polygons. That part assumes that the only thing that you have are images. But that is not always the case. Sometimes we already have a data set. It's just the data set is annotated with bounding boxes, and for some reason, sometimes business decision, for example, we would like to migrate from bounding boxes to instance segmentation. Up until quite recently, it wasn't an easy task to do, but with the release of Segment Anything model, it's actually really easy, and we actually showed how to do it fully in the UI of Roboflow annotation tool, but this time I want to show you how to do it with Python. I will use Blueberry dataset available at Roboflow Universe as an example. So here it is, quite a small, only 78 images, but the quality of the annotations is really good, and we have a lot of objects on every image. So I think it's a perfect example. We start by downloading the dataset into our Python environment. We don't need to authenticate once again because we already logged in. And after just a few seconds, the dataset is already downloaded. Like I said, pretty small. And we can find that dataset using dataset.location property. When we hit Shift Enter, we see that it's located under Content Blueberries -1. And when we refresh our File Explorer, we see the contents of that directory. It's divided into 3 subdirectories, test, train, and valid. And for the purpose of this tutorial, I will only handle the train directory, but you can imagine that you can just loop over them and process them in a similar way. To give us a little bit more insight into this particular data set, I created a cell that you can rerun, and every time that you do it, you will see a different image from that data set annotated with the bounding boxes. So if I scroll back up and rerun it, you will see a different image. Okay, that's pretty cool. Now let's try to run SAM and convert those bounding boxes into segmentations. This example is a lot simpler than the previous one. Here we only use SAM, so we don't need to use grounding DINO to produce the initial bounding boxes. We get them from the dataset, and that speeds up the process because grounding DINO was actually the slowest part of our previous processing pipeline. However, here, like you see on some images, we have even like 100 bounding boxes. So we need to loop over the bounding boxes and query SAM with every bounding box separately. And that can take a little bit of time. TQDM loader says it will take around 2 more minutes. So let's speed up that process. Boom, the processing is done. Now I can just take a look at the result. Similarly as before, I have the cell that I can just rerun, and every time I do it, it will give me different image from the data set. And you can see the masks. I mean, it's so awesome. I love that data set because it shows the true potential and power of SAM. I don't even want to imagine how much time it would take me to annotate those fruits manually. Just like before, we will save those masks in Pascal Voc XML format. Same drill, just a different set of images. But you know what? I will change the approximation percentage from 75% to 50%. So I will keep more of the points in the polygons. And that's because some of those images are actually quite low resolution images. And for them, we run into the risk of having, those triangles and rectangles that I mentioned before. We can change the project description so that it's something unique. Hit Shift Enter, create empty project. And now when we go back to our Roboflow workspace, we will see that we have one more data set, blueberries. It's empty, just like before. Finally, we can just hit Shift Enter, loop over our images and annotation, and slowly send them one by one to Roboflow backend. It will take a little bit of time for the process to complete, but we can go to the project right now and we can see that the number is growing. In the meantime, we can look at images and annotations that are already there. The first one here, I think everything is just fine. We got almost perfect annotations for each of the fruits. Let's take a look at the next one. Here, funny enough, we missed one of the blueberries in the middle, so we can just pick the Smart Poly tool from the toolbox on the right-hand side. Hover over the fruit to see the preview of our mask, and just click when the geometry is acceptable. Looks like I picked the wrong class, so let's fix that. Right click and select the proper one. And I guess that's it. It turned out to be a pretty long video, so thank you very much if you are still here. I hope that you can see how using grounding DINO and SAM can speed up your annotation process, regardless if you just have images or you have your object detection dataset and you would like to convert that into instance segmentation one. Of course, that process is not perfect and you still need to have a human in the loop. But instead of spending like literally hundreds or even thousands of hours annotating those images, right now your work for most of the use cases boils down to just clicking between images, confirming that everything is just right, or maybe adding one annotation here and there, not even close to time and money investment that you had to make up until now. And now the time has come for the announcement that I teased in the beginning of the video. Over the last few weeks, we experimented a lot with grounding DINO and SAM, and we feel that we gathered a lot of expertise with using those particular models. Those models are obviously too slow to run them in real-time environments. However, we see a lot of potential in using them to automatically annotate your datasets and use that data to train your real-time detectors like YOLO V8, for example. The coolest thing about it is that in many cases, you don't even need to annotate your data. you can simply distill the knowledge that is already in grounding DINO or SAM or other zero-shot detectors and transfer it through training process to those really quick object detectors. And we are currently building a Python library that will hopefully allow you to do exactly this with minimum effort. So stay tuned because we plan to release it very soon. But in the meantime, like and subscribe to stay up to date and maybe leave a star under notebooks and supervision repositories. That's all for today. My name is Peter and I see you next time. Bye.